Does anybody have any question for addition and subtraction of whole numbers? Are we good? Okay, so let's move on to the multiplication. Okay. Alrighty. Okay, so when we are thinking about multiplication, little kids they can relate multiplication as repeated addition. So I think it's a good idea to start from repeated addition. For example, I'm giving you cookies. I'll give Tana 2 cookies now and two more and two more. So I gave her 2 cookies 3 times. How many did I give her? We could do that, right, as 2 plus 2 plus 2, because they know the idea about the addition. They can start from addition. Then you can show that out, 2, 2, 2. You have 3 groups of 2. So we can extend that to multiplication, okay? So one definition of the multiplication is repeated addition. You can use the repeated addition model, okay? Again, for younger students, it really helps them to play with tangible objects, right? So we try to use a lot of manipulatives or actual, concrete models. So we can write 8 plus 8 plus 8 as 3 times of 8, because we added 8 3 times, okay? And the the word times, we already said 3 times of 8. So we can extend, you can link the word with the symbols as well later, okay? And you can say this 3 times 8 as 3 times 8. For younger students, it may be better to use this x as multiplication rather than dot. So yeah, I strongly encourage you to use x multiplication symbol rather than dot. Dot goes a little bit later when they go a little bit older. Okay? Or you can say it's 8 multiplied by 3. So we call 8 as multiplier and 3 as multiplicand. But again, I said this before too, right? It doesn't matter in multiplication because we can use the commutative property. So rather than multiplicand and multiplier, we prefer to use factor. Then we can say both of 3 and 8 are the factors. Okay? Because there's a lot of debate about which one is multiplier. If you search, I actually did, and a lot of people are saying, well, this is multiplier because it's multiplying number. The first number is multiplicand because it's multiplied. But some people argue the other way around. Some people are saying, oh, small number is always multiplier. So there's a lot of arguments. To reduce the arguments, we prefer to use factor. Okay, so both are the factors. And what is the answer for 3 times 8? It's 24. What do we call that? For addition, when you add 2 numbers, 2 addends together, you get the sum. When you subtract 2 numbers, first number is minuend, second number is subtrahend, right? A minus B, on your direction, I need to go the other way around. A minus B, so A is minuend, B is subtrahend, equals something, C. What is that? Difference. In multiplication, we have 2 numbers, A times B, both are the factors, equals C. What is the C called? The product. Okay, very good. So 3 and 8 are the factors, okay, and 24 is the product. Okay. Here is one model that you can use with number line. So this is different example, but if well, you can also represent 8 plus 8 plus 8 with number line as well, right? So let's look at this example with this number line. I did 4 plus 4 plus 4 plus 4 plus 4. I added 4 5 times, right? So I can write that as 5 times 4 or 4 times 5, right? And where do you land? You land on 20s, 20 here. Can you show a plus 8 or 3 times 8 using the number line on your notebook? So I want everybody to represent 3 times 8 or 8 times 3 on a number line. You got it? So in the number line, we have real number, but we are limiting the numbers to the whole numbers. So we start from 0, and you can do 1, 2, 3, 4, 5, 6. Oh, mine is too big again. Let's make it a little bit smaller. So I'm gonna start from 0. Sorry that my writing is really bad, and number line is crooked a little bit. 1, 2, 3, 4, 5, 6. This is 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Something like that. We are doing 8 times 3 or 8 plus 8 plus 8. This is 8 times 3 or that's same as 3 times 8. So probably some of you showed 8 times 3 as like you did 8 plus another 8, 8 plus another 8, 8. So each of these hop skipping is 8 and 8 and 8, right? So you did 8 plus 8 plus 8, or you can do 8 times 3, and you land on 24. How many of you did this way? Okay, is there anybody who used 3 8 times? Like this? 3, 4, 5, 6, 7, 8. Is there anybody who uses green hearts? Nobody did. I like that because this is also 8 times 3. However, it doesn't represent 8 plus 8 plus 8, right? This represents 3 times 3 plus 3 plus 3 plus 3 plus 3 plus 8 times, right? Okay, so it doesn't exactly represent 8 plus 8 plus 8. So I don't want you to use that. But the answer is the same. So you can show the commutative property here. 8 times 3 is the same as 3 times 8. Okay? All right. Any comment? Okay, and we can also do the equal groups, right? This is another common thing for the younger students. The multiplication is about coordinating numbers and sizes of equal groups. Equal groups is the key. Just like repeated addition, we add same number again and again and again, right? Similarly, we are making equal groups. So in each group, we're gonna have exactly same numbers in it. Right? So you're gonna see how many groups of how many objects in each. And the product has to be the total objects in it. Right? So let's take a look at this example up here. How many groups do we have?
3.
Okay, 3 groups. And how many objects are in each group equally?
4.
4. 4 x's are there, right? So we can say 3 groups of 4 objects or 4 x's. And how many x's are all together?
12.
12. So 12 objects, right? So the unit here is the same as number of objects. If these are the x's, you need to say, oh, there are 12 objects, 12 x's, not 12 dishes, something like that, okay? All right. So let's take a look at this example. I have 1, 2, 3, 3 dishes. And in each dish, each plate, I have 5 cookies. I can ask the question, how many cookies are there in total, right? Not how many plates are there in total. But I can ask how many cookies are in total. So how many groups? 3 groups of many cookies in
5.
each. 5 cookies in each. So there are total
15.
15 cookies. Okay. All right. You can play a lot of those. Array model is rectangular array model. So array, well, you're gonna line that up in a rectangular shape, right? So it's very similar to the previous one, like equal groups, because in each row or in each column, you're gonna have the same number, right? I have 3 rows, and in each row, I have 4 axes. So very similar, right? Okay. Rectangular array is a little bit easier for us to count because we can count number of rows and how many are in each. The number of rows show us the height, and how many there are shows us the width. So it's similar to finding the area of a rectangle, isn't it? So we're going to extend that to a rectangular area model later. Okay, so here's an example. How many cans viewed from above are shown below? Okay, so this is bird's eye view from above. How many cans are there? How many cans are here? How did you find it so quickly?
Count the amount of cans on the top row and then on the side.
And then you counted how many rows there are, right? So in each row, we have 6 cans and we have 4 rows. So even if I didn't draw, the rows like this, we know these are in the same row, and these are in the second row, these are in the third row, and these are in the fourth row. But the number of cans in each row is equal, right? They are all equal. So we can say, in each row we have 6 cans and there are 4 rows. So we can do 4 times 6. Okay? All right. So you can count it that way, or you can also see the other way around too. How many columns are there? There are 6 columns. And in each column we have 4 cans. So 6 times 4 also work, right? We didn't miss anything. Okay, so you can count the other way around. So you want to get the same number. Okay, area model. Area model is very, very useful when you have more than one digit factors. So I highly encourage you to understand what's going on here and highly encourage you to use this for your students too. Before we move on to area model, I want you to consider using the base 10 block, to show the multiplication. So because of the COVID, I don't want you guys to use actual manipulatives, but instead, how about you guys draw the base 10 blocks You understand what base 10 blocks are, right? So this is 1,000. And this is 100 flat. And this is 1/10, right? And this is 1 unit. Using this base 10 block, show 3 times 5 and try to show 23 times 5. How would you show this? Using this base 10 blocks. Consider that. And I want you guys to share. Once you are done, you can even advance your thinking as 423 times 5 using base 10 blocks. Indy and Alista, when you are done, show us how you did it, okay? When you are using the base 10 blocks, think about the place value and standard algorithm of multiplication, okay? Just like the addition and subtraction that we did with standard algorithm, remember? With the columns with ones and tens and hundreds. Okay, think about that too. Think about how we can use base 10 blocks and connect that to place value and standard algorithm there.
Yeah, you still buying that? Yeah. So then what's it cost to go to an SF, upgrade the SF3?
I'm sorry, but I love to see you guys struggling because that's what I expected.
Because I gotta do that,
How we can connect this with
right?
there's no right or wrong. I just want you guys to struggle. Okay. Is it easy to connect your model with the standard algorithm? I don't think it is, right? Most of you, I don't know how Andy and Anissa did. Andy and Anissa, can you show us your work? Just lift up your paper.
Well, I can show on the first one what I did. Yeah.
You do it anytime, all those things.
Okay. Okay, thank you. So
Mhm.
what I noticed from most of your work, you guys did something like 3, 4, 5, 3, 3, 3, 5 groups.
But you can do, there's
Many
not
of you did this way.
when to get that done.
1, 2, 3, 5 groups.
Yeah.
See, a lot of you did, right? But how is it connected to our standard algorithm? Not really. This is actually equal groups, right? Or repeated addition there. So using, I just wanted to see you guys are struggling and I wanted to show you it is not easy to use this standard, base 10 blocks to show standard algorithm. So here, what I'm gonna do is I want to introduce you
Alright.
area model. This is very, very helpful for the older students to extend from, you know, 1 digit by 1 digit to 10 digit by, I mean, 2 digit by 2 digit or 2 digit by 1 digit or much, much, much more. So let me show you. No, not this one. So for example, 3 times 4. The area model is you're gonna make the rectangular shape. Okay, and then we're gonna see what the area is. So for example, you have 3 by 4. 3 by 4, you already know 3 times 4. Let's say your students don't know 4 times yet. Okay, they only know like 2 times. Then they can break this into 2 by 2 and say 2 times 3 is 6 and 2 times 3 is 6. And total is 6 plus 6, which is 12. If they already know they can, you know, 4 times, they can just multiply 3 times 4 as 12. It's fine, right? Let's think about extending this as something like, what was the next problem I gave you?
3 times 5.
3 times 5, and then
23 times 5.
3 times 5. Let's consider 23 times 5. What you can do is you can show 23 is 20 plus 3. We can break that up, right? 23 to 20 plus 3. So what we can do is we can make 20 as 10 and 10, and 20 can be broken into 10 and 10. 10 and 10. So 10, 10, and 3. 10, 10, and 3. And the other part, you have multiplied it by 5. So if I draw it this way, let me erase down here. This is what I got, and it shows 10 plus 10 plus 3, which is 23, right? So we have 23 times 5. And they don't know how to multiply 23 times 5, but they know how to multiply 5 times 10. 5 times 10 is 50, and 5 times 10 is 50. 5 times 3 is 15. So they can just add all of those areas together. Okay, 3.
Good. Plus 3, not plus 15.
Oh, plus 15, thank you. So it's gonna be 115. Right? Using the area model, you can always extend this. Think about, what was my third one? 20
It was 423.
times 5, I believe, 5. If you're doing that, you can do 400. There are a lot of different ways. 400 plus 20 plus 3, and think about times 5. Or you can do 100 plus 100 plus 100 plus 10 plus 10 plus 3. It doesn't matter. It just, we just have different breakups here, right?
bring it
If
home?
we are doing,
Should be downstairs with the rest of his stuff. I don't know if he brought it home.
Sticking off, let's get your stuff.
the ending, can you, yeah, mute?
Sorry. Yes.
Okay. This doesn't have to be exactly broken. We can just indicate this is 400, this is 20, and this is 3. And the other side, you can say that's 5. Then you can find the areas there. 4 times 5 is 20. 400 times 5 will be 20 hundredths, right? 20 times 5 or 2 times 5 is 10. So 10 tens, which is 100. And you can do 3 times 5, 15. You can just add them up, right? If you are doing times 2 digit, can I erase it? It's okay? Okay. For example, 23 times 68. Let's think about 23 times 68 or 68 times 23. What I can do is I can break up 23 as 20 and 3, right? And the other side here, the length is 60 times 8. So you can make a rectangle there. Well, to be more accurate, you can make this much longer than 23. Okay, I'm just making the rectangles here. So here, we are making 4 tinier, smaller rectangles there. And you can find the area for each of these rectangles and add them together. So what we have here is what? 20 times 60, 1200. 3 times 60, 180. 20 times 8, because this length here is 20 and that length is 8. 20 times 8 is 160. 8 times 3, 24. And then we can add them together. I want you to look at this problem again. Think about the standard algorithm with you. Before we move on to standard algorithm with all the moving, carrying over, we can do the partial sum, right? So let's look at 3 times 8. What is it? 3 times 8. 24. 20 times 8. Or 8 times 20. So we did this part, and what's this part? This is not 2, it's 20. So 20 times 8 is 160. How about this part? So we are done with this. Now we can multiply with 6. 6 times 3 is 18, but this is not actually 6, it is 60. That's why we put 0 there. So 6 times 3 is 18, but 3 times 60 is 180. Does it make sense? Okay, now 6 and 2, but this is actually 60 and that's 20. Not 6 and 2, right? So 60 and 20 makes 1200. Right? And then we can add them together. So we know the procedure there, but I want you to pay attention to the numbers here in the partial sum with the numbers here in the smaller rectangles areas. Do you see anything in common? What do you notice? Compare those numbers. What do you see? Do you see 24 here? Yeah, right here. Do you see 160? It's right there. 180? Right here. 1200? Right here. So it's exactly same as we are adding these areas together. That works because we broke this into each digit. 23 as 20 and 3, 68 as 60 and 8. So the partial sum of each of these digits multiplied together should be same as the area model. Okay, so they can use the rectangular area, okay, instead of this. But then you can connect that with partial sum so they can understand why they get the numbers here. What is this? 16? And you have 1 there. So what is that? 6? No, 5. So that's the total number. When you add these together, you're gonna get the same number too. So you can always extend, this rectangular area model. Let's consider 3 digit by 3 digit. Can we erase it? So think about 3 digit by 3 digit. Let's make a number. Let's do something like that. If you are using standard algorithm, what happens? It's gonna be very, very lengthy, and there's a lot of carrying over and stuff. So it's not gonna be very easy, right? So for those students, they can use rectangular area model. So they can break this into the digits. So 234 is 200 plus 30 plus 4. Then they can see 500, 19, which is 10 and 9. They can break, rectangles like this. And fill up each of the rectangles area. So I will let you finish this one and find the product of 234 and 519. So find the area for each of these 9 rectangles. Show me your thumbs up or your none. I need to take a picture of you guys working hard. You are so beautiful. I love this. When you're multiplying, pay attention to the digits, okay? About 10 more seconds. Okay, starting from Morgan, can you give me the answer for each rectangle area? What did you get here? 100,000? Is that how many zeros you have?
Yeah. Exactly.
How did you decide the number of zeros there?
5 times 2 is 10. And then
5 times 2 is 10,
and you have 4.
and you have 1, 2, 3, 4?
Yeah.
Okay, very good strategy. How many of you use the same way? Okay, a lot of you did. Okay, awesome. Okay, good, good, good. Yeah. Yeah, for the bigger numbers, it's hard to, remember, oh, this is 200 and 500, so it's not easy. But you can also think about it this way. 200 times 5 is what? 0, 0, 10. So we know it's 1,000. If you have 50, you're going to have 1,010. And if you have another 0, you're going to add another 0 because we have hundreds there. How many hundreds are there? 1,000 hundreds are there. Okay? So you can actually count the number of zeros there too. Okay, very good. Okay, let's move on to Brianna.
So what I got was 1,500, or no, 15,000, sorry.
15,000, very good. So again, you can just multiply 3 by 5, 15, and you can count the zeros, right? 3 zeros, awesome. Hannah? 2,000. Because 4 times 5 is 20, so you have 2 zeros there. Awesome. 2,000. If you have different answer, please jump in, okay? Okay, if not, we will just keep moving on. And next,
300.
300. Oh, just take a look. 4 times 10. What comes here?
40.
40. Keep going.
1,800.
1,800. Because 2 times 9 is 18. And you have zeros. 2 zeros. Keep going.
270.
270. 36. And then what can we do? We can just add all of this together, right? One strategy, you can add, the rows, and then add them together, or columns, and add them together, okay? So there are a lot of strategies. They all work. It doesn't matter because in addition, we can do the commutative property. We can switch them around, right? Okay, so in total, what did you get? 120, 21,446. Everybody? Okay, I saw a lot of nodding, so sounds like this is the answer. So you can always extend the digits. You can do 4 by 4, 5 by 4. I think this is so much easier for the students to understand what's going on there than standard algorithm. But once they know this one, what's going on there, they can, use a standard algorithm. Because now we know we have to multiply each of the digits with the other one using the distributive property. So 4 times 9, 36. 3 times 9, 27. 27 and 3 is 30. 2 times 9, 18. So it's 21. Here, what I want to focus is, the number that you are carrying over. Recently, I had one research and looked at the students' mistakes about the place value. So when they were doing 5 times 9, 36, you usually write it here, don't you? Right? I like that because its tens place is 36. How about this one? 3 times 9. Sorry, it's a little bit off. My handwriting wasn't really good. I don't know, actually, make it clear. So let me rewrite that. So ones place, tens place, and hundreds place. And then when you're doing 3 times 9, it's not actually 3. It's 30. 30 times 9 is what? 27. So the 20 doesn't go here because it's actually 200, right? So you better write it up here. And that 7 is in the tens place. So 7 and 3 together is 0. Does it make sense? And you can change this to 3 in hundreds place. But a lot of fifth grade students that I studied, they put that 3 again up here and again up here. Everything that they carried on was above the tens place. That misled them to wrong answer a lot of times. So I want you to focus on what the place value is when you're multiplying those numbers. So for example, 3 times 9, this is not 3 times 9, it's 30 times 9. So it's actually 360, not 36. Does that make sense? Okay, pay attention to that. When you're using this model, you can reduce that error. But once they already know this one, they can move on to standard algorithm. But before they use standard algorithm like that, I think it really helps them to think about the partial product, so they can pay attention to the place value. Okay? Any comment? Okay. Any question?
We continue that problem?
Yeah, we need to continue.
Okay.
Yeah, I will just let you do that because you know how to do that right now. And we already have the answer, right?
Yes, but mine are completely different from what we,
Where?
like the multiplication and the addition are completely different.
So what is different?
the end product.
You didn't get this one?
No, when I multiplied, I didn't get that one.
When you're using the standard algorithm, you didn't get that?
Yes.
Okay. So let's take a look at this. 234. Well, actually, I'm gonna just erase this part here and we're gonna work on that, okay?
So I keep thinking that I did something wrong, so that's kind of why I'm asking.
Yeah, so when we have more digits, even we get confused, right? So it's a good idea to work on that. And we move this here. Okay, so let's take a look at 234 times 519. Okay, I prefer to use a partial sum. Okay, so let's do that. 4 times 9, 36. You can see we have that number here too. And what? 9 times 3, 270 is 30 times 9. And 200 times 9, or 200 times 9. So we know it's gonna be hundreds. So I can put 2 zeros, and 2 times 9 is 18. So it's 18 hundredths. And here is tens. So we can just count how many tens are there. 4 times 1 10, 4 tens. 30 times 10. So it's gonna be what? 300? I just did this part, right? And then we have 200 times 10, which is 2000. So we are done with 19. Now we need to move on to 500. This is hundreds. So we're just gonna start from 100. 5 times 400, which is 20 hundredths. 5 times 3. Oops, bless you. So this is 100, so we know it's gonna be 0, 0. And this is 30, so there's another 0. 5 times 3 is 15, so it's gonna be 15,000. The last one, we have 500 and 200, so we can count as 100 and 100. And 2 times 5 is 10. Then add them together. This is exactly the same number as the partial sum here in the area. So we can see, oh, we have this one here, 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 and we have 40 here, we have 1800 here, 270 here, 3060 here. So we have all the numbers exactly same. So when you add this together, you're gonna get exactly same.
Okay, I see what I did wrong on mine, so that's,
Awesome.
I just figured I would go over it because it was like, wait a second.
Yes, yes.
Yeah.
Uh-huh. Yeah, I love to find your own error. I think it's really critical. It's very important. Okay, any other question or comment? Shall we move on then? Okay, so again, area model is very useful, right? And you can always extend that to bigger models, okay? All right. Okay. Another model is Cartesian product model, or another name is ordered pair. We are familiar with ordered pair with the x value and y value in the parentheses, right? So this is more like for ordered students, but when you are given counting problems using fundamental counting theorem, this is very, very useful. So some examples like this, the student wants to choose shirt and pants. I believe you saw this kind of problem a lot of times. And how many different, options does he have? Something like that. So let's say Alyssa has 7 shirts and 3 pants. How many combinations can she have? Things like that. We have seen that a lot of times, right? Okay, so in that case, this ordered pair helps. For example, there are 3 types of bread to choose from. So wheat, white, and rye. And there are 4 types of cheese to choose from: cheddar, provolone, Swiss, and American. How many types of cheese sandwiches can the restaurant make with these choices? So what's your strategy? What's your strategy? How many of you want to write down as a Cartesian product like this? With white bread, you can have cheddar, provolone, Swiss, and American. Can you interpret what's going on here? Take a look. With white bread, you can have cheddar. With white bread, you can have provolone. With white bread, you can have Swiss cheese. With white bread, you can have American cheese. So we have all the options for white bread. If you have wheat bread, you can have also cheddar, provolone, Swiss, or American. With rye, you can have each of those cheese as well. So you can understand what's going on here in the table, right? So this is one option that you can do. Another way is called tree diagram. I believe you are familiar with this one as well. So with to make sandwiches, you can think about bread. We have white, wheat, and rye. So you can make 3 branches there. In this tree, you have 3 branches, big branches. For white bread, you can choose 4 different types of cheese. For wheat as well, 4 different types of cheese. For rye, you have 4 different types of cheese as well. So either you use the table or you use the tree diagram. You can have the pairs like this, right? White cheddar, white provolone, white Swiss, white American, with cheddar, right? You can take a look at that. How do we count that? You're gonna count all the way there, but we already know what's going on here. So actually you can just do, there are 3 types of bread. So we can make 3 groups, each bread groups, and in each bread groups you can have 4 different types of cheese. So in each group you have 4 items in it. So it's exactly the same as 3 groups with 4 items. So we can do 3 times 4 as total, right? Okay. So either you can use a tree diagram or the pairs like that in parentheses. You can do that. Or you can even make a table. But that's also multiplication. Okay. So those are the models that we talked about today. Let's move on to properties quickly because we already know a lot of these properties. In addition, we learned that, right? So closure property. Hey, let's think about closure property. What does closure property mean? So you pick any numbers, right? From 4 number, multiply them together. Is this still whole number? Then it's closed, right? So closure works. So pick any 4 numbers. 0 times 2 is 0. 1 times 2, 2. 10 times 90, 900. They're all 4 numbers. So it works. Combinatorial property, 2 times 3 is 6. Switch them. 3 times 2 is also 6. So exactly the same value. So combinatorial property works. Associative property, you associate this first or the other first, same number. So for example, 2 times 3 times 4, 2 times 3 is 6, 6 times 4 is 24. Or 2 times 3 times 4, 3 times 4 to that first, and you get 12 times 2, 24. So associative property works. Identity property, you get yourself. A times 1 is A. Whatever number times 1 is itself, right? Okay, so for these 4 is exactly the same as addition, but we're gonna add one more. Property of 0, multiplication property of 0. Whatever multiply and by 0, you get 0. All right, that's it. Okay, have a good day, guys, and keep an eye on my email.